This is AP Review Chapter 3, Lesson 2. Here we're going to take a look at a free response question, and for this one we could use the calculator. So go ahead and take your calculator out, and you'll be given some numbers that we'll have to calculate. Now this is going to be another empirical formula question. So empirical formula. So we'll be using the poem for the empirical formula that we reviewed last time, percent to mass, mass to mole, divided by small, and then multiply till whole. So let's take a look at what we've got here. We have a compound containing the elements carbon, hydrogen, nitrogen, and oxygen, and it is analyzed. Usually it's analyzed by breaking the compound up and finding how much of each of the element you have. Here it says when 1.2359 gram sample of it is burned in excess oxygen, we form this much CO2, and then the combustion analysis also showed that the sample contained this much hydrogen. The first thing it wants us to find out is how much carbon there is in our original sample. Now very oftentimes what they do is they'll burn, this is a hydrocarbon, they'll burn it, and during the combustion all of the mass from the chemical compound went into CO2, all the carbon, went into CO2. So capturing the CO2, if we can find out how much of this is carbon, we'll be able to find out how much carbon there is, because all the carbon went into carbon dioxide as we burned it. So, knowing that we have a total mass of 2.241 grams of CO2, if we can in effect pull out the carbon, we'll find out how much carbon there is. And this is actually quite simple to do. What you have to realize is that every amount of CO2 has a certain percentage of carbon in it. The way you can find that out, if you can take the grams of carbon divided by total grams of CO2, total grams of CO2, and you'll find the ratio of carbon that's in your compound. What we did usually is we multiply this by 100 to find the percent of carbon, and then you can use that percent to pull out. So why not we just multiply directly? Multiply 2.241 grams times the ratio of carbon to total CO2. Now carbon's mass is 12.01 grams. The total mass of CO2 is 44.01. So you'll have to take a minute to calculate this out, but this is total mass of CO2 and this is just mass of carbon. What we're doing is we're essentially multiplying the grams by the ratio that is carbon. So this will be able to pull out the carbon out of the CO2. So go ahead and do this calculation and see how many grams of carbon you find out, you come out with. So do 2.241 multiply by 1201 divided by 4401. And you should get 0.6116 grams of carbon, and that would be the answer. So this is actually a very useful technique of pulling out the mass, because the mass percent that we get here is the percent based on mass of carbon. Okay, here the next part says when the compound is analyzed for nitrogen content only, the mass percent of nitrogen is found to be 28.84%. Determine the mass in grams of nitrogen in the original compound. Oops. Now this is actually even simpler than part 1. All we have to do is apply 28.84% to the original mass of the compound. So why don't we convert the percent back into decimal form? So we got 0.2884, which is percent back to decimal. Just multiply that by the total mass of the compound, 1.2359. Really, we're doing the same thing we just did for the carbon dioxide, except the percent was given to us here for the nitrogen. So just multiply these two, and you should get yourself Go ahead and do this calculation and see if you come up with 0.3564 grams of nitrogen. So this one's very similar to the first question, but even simpler. Okay, and then we're asked for the mass of oxygen in the original compound. Now we were given the mass of hydrogen. Since we have 3 of the masses, all that's left to do is just subtract from the total these 3 masses. This mass, and this mass. So it's really 1.2359 minus the total of the others. So put hydrogen in 0.0648, put carbon in 611.6, and put nitrogen in 3564. And take a minute to do this calculation. Again, you're allowed to use the calculator on this part. That's why the numbers are tougher to work with. So go ahead and add these up. 0.0648, 611.6, I would recommend using your calculator carefully here and make sure you got this amount. So we have 0.2031 grams of oxygen. And on the next slide we're actually going to use these values to do some calculations. So go ahead and make sure you can see these. Let me jot them down. And we're actually going to use these to determine the empirical formula. And hopefully it'll work out. So we're breaking it down. Now we know the grams of each of the compounds, or of the element in the compound. So we know we've got the percent to mass, essentially. And next we're going to try to solve for the empirical formula. So let's go ahead and do that using this poem. So begin with those 4 substances. So we had, for hydrogen, we had 0.0648 grams. For carbon, we had 0.6116. For nitrogen, we had 0.3564. And for oxygen, we had 0.2031. Now remember, it's percent to mass. Oops. Then mass to mole. Divide by small. Then multiply till whole. So we're going to do the mass to mole step next. Let's go ahead and let's convert all these into moles. And that's done by simply dividing them by their molar mass. Grams of hydrogen down below, a mole of hydrogen up above. Hydrogen is 101. Do the same thing to carbon. A mole of carbon is 1201 grams. It's going to get a bit sloppy here. A mole of nitrogen is 1401 grams. And a mole of oxygen is 1600. So go ahead and do each one of these and quickly work out the moles of each substance. So, and use significant figures. Keep a little more significant figures than needed until the very end. So we have 0.0648 divided by 101, which gives us 0.06416. This is moles of hydrogen. Do the same thing with the carbon. 0.6116 divided by 1201 should give us 0.05092 mole of carbon. Do the same thing to the nitrogen. Which should get us 0.02543. 44 if we round. Mole of nitrogen, and the last one, oxygen, 0.2031 divided by 16. Should get us 0.01269. Notice I've kept 4 significant figures in each one of these measurements, and this is recommended because if you round too many times early, then you're going to compound your error. So mass to mole is good. Next, let's go ahead and divide by small. Let me do this in a different color. The smallest number here looks like is the oxygen, so we will divide everything by 0.01269. 0.01269. 0.01269. And this will give us the rough mole ratio of these. Oxygen obviously becomes 1. And the whole point of dividing by small is so that you can get the small number to be 1, and then everything else in a ratio to that 1. So for the nitrogen, we've got 0.02. You can kind of see that it's twice as much. So you can kind of see that it's a 2 to 1, so you get roughly 2 moles of nitrogen. For the carbon, it's kind of hard to see, so here let's go ahead and divide. We got 0.05092 divided by 0.01269. So here we got roughly 4 moles of carbon. Actually, you can kind of see this. That's right, because we have 12. 4 times 12 is 48, but we have a little more than 12. We have a little more than 48, so 4 times. And then finally, this one looks like it's probably going to be roughly 5 or 6. Let's go ahead and divide the carbon as the hydrogen as well. 0.06416 over 0.01264. This one gives us 5 moles of hydrogen. Now, you did not have to use the last step because all of the numbers are whole. If, however, you had a half number, say if hydrogen was 2.5 or something, then you'd have to end up multiplying everything by 2, and you would have to make sure you multiply absolutely every element by that many numbers. But because we don't have any half numbers, we don't need to worry about that. If you had if carbon was 1.33, you have to multiply everything by 3. If something was 1.66, you have to multiply everything by 3. So in other words, you have to multiply everything to get it to a whole number, depending on the fraction that you end up with. So in this case, our hydrocarbon formula, so we have HCNO. Looks like we have 5 hydrogens, 4 carbons, 2 nitrogens, and 1 oxygen. H5C4N2O. And then at this point, it doesn't really matter which order you write it in. Usually hydrocarbons are written carbon, then hydrogen, then nitrogen, then oxygen. So you can say C4H5N2O. But this would be sufficient for the answer. Okay, and the very last part here deals with something called the molecular formula. What we've done here, this poem that we've been using is for empirical formulas, which, remember, is the most reduced version of the formula, the lowest whole number ratio. A molecular formula is a higher formula. In other words, it's the formula for the molecule as it really exists. So a molecule can be twice as high or 3 times as high. So like a CH2O would be an empirical formula, but this could actually be C6H12O6. This would be the real formula. This would be the molecular formula of the compound. The empirical simply shows us the ratio of the atoms. So now we're saying here's the empirical formula. It's a 1 to 2 to 1 ratio, and the empirical formula's mass is 188 grams. So the idea here is CH2Br has a mass of some sort of mass, and the real formula has a mass of 188 grams. So let's find out the molar mass of CH2Br, and we'll stick that in here. So carbon is 1201, carbon is 101, and bromine, if you look, is about 79.9. So if you add all this up, we have a 9 here, we have an 11 here, we have a 12 here, don't we? 9 plus 3 is 12, and we have 2 So you have 92.91. So this is roughly 93-ish, roughly 93 grams. So because the empirical formula has a mass of 92, the molecular formula has a mass of 188, you can kind of see that it's roughly 2 times as big. So going from here to here, it's roughly times 2, which means our molecular formula is also going to be 2 times bigger, or C2H4Br2. So this is a quick review of the molecular formula, how to get the molecular formula from the empirical formula, and it's as easy as seeing how much bigger the empirical formula, the molecular formula is, and then multiplying the formula by that many. So this concludes for us lesson 2 of chapter 3 AP review.